What you said? What should I do? Yeah, good morning, ladies and gentlemen. I don't know how many people are there. All I can see is 9 connections so far. So let me start off. This is in advanced, in packaging material analysis and testing. So what I will do is that I will go through the basics of absolute basics pretty fast. What is a package and a packaging material, and what we basically look for when we are talking about a package, and to ensure the performance of the package, what all we decide to do and test to ensure that, right? So essentially, when we think of a package, we think of metal containers, glass, wooden or plastic containers. Per se, for a person who is not related to packaging, will think of this. Now, so if I just think of a definition, is basically the science of protecting and carrying food from, the manufacturers to the distribution and to the end users. Right? So we say that it's a coordinated system for preparing goods for transport, warehousing, logistics, sales, and end use. So that's what packaging is. And when you say packaging material, any product, any material that is used for making a package, constructing a package is a packaging material. Now normally packages are of 3 different consistencies. One is called a rigid packing, which is glass bottles, wooden crates, metal containers, even strong cardboard containers are rigid. There are some semi-rigids which are made of boards or formed plastics. And then there is a flexible pack, which is the most popular and gaining popularity day by day. The basic difference between these 3 is that rigid containers have a specific shape. So is semi-rigid, but semi-rigid containers sort of easily get deformed under small loads. But flexible packages are something which is by its name flexible, and it covers and hugs into the product. So I am basically from Bhutamaki Paper Products Limited. We are into flexible packaging material production and giving services related to that. So what I will be covering is on flexible packaging. Now, per se, if you say that what we are looking for a package, it needs to carry the product, it needs to communicate, it has to have something inbuilt in it so that the end user who is using it has the convenience of dispensing, disposal, handling, right? And then any package has to conform to some legal needs or provide some security features. Considering all things done, then we have to have something which helps us to convert a packaging material into a package. Like a flat sheet of laminate or paper or whatever you say, or a film, must create sort of a enclosure which will contain the products. Right? Now, when we say carry, what is a carry? Carry is, the macro carry is simple, that we understand that there should not be any spillage from the material, or there should not be any contamination coming from outside into the bag. It's primarily the mechanical strength of the package. What is a micro package? Micro carry is that the gas, moisture, vapors may pass through the package and come in contact with the product inside. Now, if the products are sensitive to such moistures or gases, then we have to ensure that we don't allow this whenever it is necessary. Okay, so that we normally call barrier properties. And then there are some special needs which are coming in advanced packaging materials, is that we add flavors to the package material so that the flavor in the product is enhanced, which is provided by the packaging material. We sometimes need to return a special atmosphere for the health of the product. And sometimes we need to allow conditional breathing. I try to put some photographs at the bottom. You can see that, those vegetable packs has holes in it so that the moisture can go out. Not only moisture, gases also. Okay, so that was carry. Convenience. Convenience includes dispensing need. A very good example is Kinder Joy. It's an egg. You try to tear them apart. You get into two containers. You get two containers in your hand, still closed, packed. Then you can easily peel off the lid from the containers so that you can get either the toys or the foods. And in one of the lids, there is a spoon provided so that you can eat the chocolate. You see the way it is designed, then that it doesn't open up when you are trying to separate the two parts. The lids are intact, so you can only remove the lids when you want to. Then there are simple dispensing things like providing a handle or a spout. What we normally don't see is that in the back end of the stores or this malls, there are places where bags are stacked. Now, if the bags are very slippery, then it will be very difficult to stack them. It will fall. So when we are designing our packaging material, we have to take care of that. Good displays, attractive packages, important. Then we have single dose packages where the customer did not think of anything, just tear open the back and put it in a container, and he has the dose. It can be a medical product, it can be a beverage, it can be anything. Okay, communicate. Now, a good looking packs can always communicate a lot of great things. It is a point of sale ad, a new product launch with a good packing design attracts customer, and they can just give a first try, and if the product is good, it is through. And then the statutory requirements are also printed. So the pack has to have the ability to carry good prints onto it and shapes also. Conformance. Depending on the type of product we are packing, there are different types of conformance it has to go through. One is the process, how your packaging materials are produced. There are legislations, standards available. You have to comply to that. For the materials of construction, like if you are packing food products, it has to conform to certain basic needs, which are guided by USA FDA, EU. There are Indian standards also. So you conform to that. And if a security feature is also need to be built in, it has to conform. So considering all these things, all these basic needs, packages come in many formats to ensure to comply those needs, whether it is looks, whether it is dispensing, whether it is a carrying strength, everything. Of course, considering the economics of the whole thing. So, you see the basic requirements of a flexible laminate is that aesthetics, strength to withstand and handling transportation. We have discussed this. Provide shelf life. That restriction of allowing gas or moisture passing through it. Maintain flavor and add taste. Maintain flavor and taste of packaged foods. Simple things. I'm just you know, put them in a single piece of paper. Conformance to statutory and other requirements, facilitated creation of container dispensing is. This is from the producer's point of view. The first 4 points are basic requirement of the package. Now you designed a packaging material, but then you have to create something on it. You have to provide something on it so that a container can be easily made out of that. And finally, the most important is economics. So what we do is that we take different substrates or different materials to achieve this desired property within the economic scope. So that each of these different materials provide certain properties to the packaging material and it conforms to the intended use or the need. So, after doing all these things, after we decide what the needs and requirements are, but to ensure that a packaging material, like any product per se, conforms to the need that we have identified. So, there are many definitions of quality. I've just put one such definitions. Quality is basically conform to the need. So we have identified the needs. Now we have confirmed, we have to do something so that these needs are catered to. So we have to do, to start with, on the design part of it. And once we do that, once we do a design, theoretical design, we have to ensure by testing this material that it conforms to the needs. So that is, testing evaluation is necessary to assure and conform to the quality needs at different stages. Most important is the assure part, because it's no good testing a material, rejecting it, that it's not conforming to my needs. So the definition of the need is the most important thing. What my product need from the packaging material. Then design ensuring all the needs that we have identified are met. And then after making, test that it's true, and to control unwanted variations in the processes. You test it just before using or at the time of using. We'll just discuss how you do that at different stages. So, testing at design level, quality assurance. We know what we are going to pack. So, the first thing that comes in, the primary carry, the macro carry, the strength of the material. So, the strength and elongation of the material, I will tell you what is an elongation is if you don't know by chance, is being tested. Cold or heat seal strength. Like after making a packaging material, when you are trying to make a container, it's normally sealed to make an envelope or a box or a pouch. So what are the strains that you can create which will ensure that the product carrying is performed? That strength. Interlayer bond strength. As I mentioned that we use different substrates and different materials to provide different, to build in proper, different properties of the material, indented need of the material. So, and these different materials are kept together using adhesives and different methods. Now it is important that they are kept together with a certain strength so that they don't get delaminated or they just don't go away from each other at use. So that is interlayer bond strength. Tear resistance. How much resistance this material gives when you are tearing it open? Actually, the most important thing is that many times we have seen that when you are trying to tear open a particular pouch, we are actually fighting because the tear strengths are too high. So you need to reduce that. But there are applications, there are points. If I reduce the tear strength to a very low value, it will not serve the basic need of macro carry. Impact resistance, opaque material can fail. Can fall. If you just drop it from your hand, it should not burst off. So that's impact resistance. Puncture resistant products, if they're sharp, have protrusions like noodles, vermicellis, some vegetables, meat, which can have sharp protrusions. So you have to build up a puncture resistance of this material, which probably is not necessary when you are packing a liquid or a powder. And then inflexible packaging, thickness control is being done from a design level, within how much tolerance it can go, because from a flat film or a sheet, we create a container of a particular size, a particular volume. So the dimensions, length and width are controlled. Now the strength of material will definitely depend on this length and width and the thickness of the material. So as the length and width are not in our control, because that's controlled by the volume of the material, volume of the pack that we have to create, we control the thickness of the material. How we do that? So there is something called a universal testing machine where we check the tensile strength. At what load it, tensile load is tears off. Heat, cold seal strength. As I said, that when I'm trying to make a container, I join the two surfaces, which I call normally it's been done by applying pressure when it is hot, or sometime with a specific sealant used, you can do it in cold conditions also. What is the strain that is giving? Tear resistance I just explained, and puncture resistance I just explained. All these things can be done with the universal testing machine. How we do that? We put our specimen clammed between two jaws and separate the jaws, and note down how it is behaving at different stages of elongation, and at what load it breaks, and it breaks after elongating how much. This is the value we capture. From there, we can declare the tensile strength of the material, which is in Newton or in kg or in grams per square millimeter cross section of the material we are testing. And there is something called there is something called a breaking load. What is a breaking load? Is that under what load a 15 millimeter wide sample is broken. As I was telling that it is a flexible materials, normally 100 thin materials. Sometimes erroneous stiffness measurement by some operator can give you a wrong data. So it's a practice to declare the strength per 15 millimeter. A designer gets a better feel of how the laminate or the material is going to behave. And elongation, as I explained, that what after elongating it to how many times of the original length it breaks off. So E is the stress strain that has happened, the deformation that has happened, and L is the original length. So the ratio of that in percentage is called elongation. Now in bond strength, what we do is that use the same machine. Because it's a multi-layer laminate, as we call it, we manually separate the two ends by some means, by using some solvent sometime, and clamp the two substrates in the two jaws of the machine, and once again separate them and decide or note down what is the load taken by this laminate to separate. That comes in grams or Newton for 15 millimeter. Heat and cold seal, what we do is that we just take a sample. You can see a sealer on the right hand corner of the slide. We use a heat sealer. If we put heaters off, then it's a cold sealer. So there are two jaws which are actuated by pneumatic pressure. So you can control the pressure that is given, the top and bottom jaws, and you can keep them to the up to a time which is called a dwell time, for which the jaws will remain closed. Okay, and then we plot or we take different values of the seal strength. The seal strength is measured in the same way I have explained you. We are doing the bond strength. We put clamp the two free edges of the sealed material in the UTM machine and separate them in a particular speed and check how the loads are coming. So at different temperature, latent temperature are actually the temperature of the sealing jaws, and we separate them and see what are the loads which is coming, and Newton per millimeter, it can be Newton per 15 millimeter. It depends on the contract between the manufacturer and the end user of this material. And you can see that in this plot, it has mentioned the sealing pressure and peeling rate. So at what rate it is being tested and what pressure it was sealed, these are all defined, because in a change of sealing pressure, the seal values may differ. So this is other variation against pressure. When you are actually, you can plot it for heat seal also, but when you are doing a cold seal, this is how you can check at what pressure the seal is initiated. In this plot is closely some 1.3, 1.4 bar. So from there, this laminate behaves like this. It goes down a bit and then goes up. So these values will ensure when you are making a container out of this packaging material, your closing areas are having enough strength so that it can perform to its end need. Then there is something called a drop resistance. Drop resistance, as I said, that is an impact load that comes in, and if you plot a material, you probably will get this side is strain, this side is stress, you get a curve like this. Up to this level, when you are loading this material, there is a deformation that is happening. So this is the deformation that is happening. But if you release that load, it goes back. So this is the elastic limit. So this area, this energy is called resilience. And after that, it deforms, but it doesn't fail because the failure happens here only at the end. So if the toughness value is very high, then even if you drop it, it may get a bit deformed, but it will not burst off. So you can see the drop strength or the strength, impact strength, resistance against failure in impact loading like drop, not only depend on the strength of the material, but also depend on how much how much it can elongate before getting busted. So this area is a toughness. Okay. Then tear resistance, as I explained you a bit, why tear resistance is important. These are tested in two different valves. One is called a Towser tear and it's called a Elmendorf tear. Towser tear is once again done in a UTM machine. You can see the red sample clamped into grips after creating an initial tear, and when the tear propagates, we can check that how much load it is taking. For an Elmendorf tear, it's under impact. This semicircular body is a weight. So this you can see how it has clamped and teared in Elmendorf. So we clamp this to create an initial tear, clamp them, and allow this material to drop very fast. And we note down how much resistance this material has given against tearing. Impact resistance. So this is actually called a dart impact tester. We drop a weight that is in the left and top with a hemispherical bottom from a height, and see, and the sample film or laminate or paper or whatever it is been clamped at the bottom, and it is dropped, and see at what weight the failure of the film happens. We don't change the height normally. There are two fixed heights. What we keep on changing is the load that is applied onto this. And at a particular load, when 50% of the sample passes and 50% of the sample fails, because there is always a minor variation in thicknesses and properties of the laminates. So that is a value that we consider, and from there we actually get a feel of the toughness of this material. Puncture resistance, a typical tool for measuring puncture. This is also done in an UTM. So you have a special attachment on it, which has a sharp needle at the top and a holding device at the bottom. And this needle comes down and tears or punctures the sample. And we note down the maximum force required at break, because it may vary depending on the property of the material, penetration distance, and energy to break are determined. I mean, energy is the distance, force taken, and the distance travels. From there, we can make an assessment of how much energy it can absorb, how much resistance it can give against against puncture. Okay, so that was macro, basically the strength of the package. Then this is also a QA part, is a barrier property. Now for the packaging material, how much resistance it can give for moisture to pass through it. It's called MVTR. Then there is something called OTR, which gives an indication of how much oxygen resistance to oxygen passes through the packages. Then there is something called a migration and leaching, which is extremely important for food and wrap products, where if the packaging material allows some of it contains to come into the product pack, which is a food or a drug, then it is bad. I mean, it cannot probably be absolutely zero, but it has to be within a particular limit which has been established, so it's safe to use. On the other hand, the packaging material can absorb material from the packed material. We have just encountered one of this problem in packing a pharmaceutical product. One of the constituents, important constituents which are present in a very low percentage, were getting absorbed into the polyethylene film that we are using in the inner layer, and the product was losing its efficacy within 2 to 3 months. So that's a problem. And then compatibility and stability. Now these are very specific: migration and absorption, or leeching, scalping. Now after all things, when I pack a material in a packaging material, you need to understand after its targeted shelf life, both the packaging material and product should remain suitable for its intended application. So we do a typical stability study at a little higher speed, so that like if the shelf life is 2 years, we don't need to keep the material for 2 years. I mean, I understand that people are there from food packaging, so you all know what is a compatibility or stability study. But a packaging material supplier, we normally test his product, normally test his packaging material, not the product, because they are not really knowledgeable and equipped to test the product pack. Okay, so how we test a barrier property? You can see the central brown layer, which is a test film. From one side, we allow a gas to come with moisture. We can control the RH of this, relative humidity of this material, and from the other side, a dry nitrogen comes in. Now, if the moisture passes through this film, test film, it gets mixed with the nitrogen, and the moist nitrogen goes out, and there are sensors who can actually probably test each molecule of the moisture, and over a period of time, and this test continues. When it's stabilized, we can calculate out how many grams of moisture passes through this test film per square meter in a day at a particular temperature and relative humidity. That's how the MVTR values are declared. Similarly, if you replace this moisture by a pure dry oxygen, I mean, it's not necessarily dry, and that depends on the test condition, test RH. And you allow oxygen to come from this side, and dry nitrogen, oxygen-free nitrogen, carefully oxygen-free nitrogen passes from this side. The oxygens will mix with this nitrogen. Once again, the sensor will identify that. So we'll be able to find out cubic centimeter of oxygen passes per square meter area of the test sample in a day at a particular temperature and RH. One thing is important to remember, depending on the RH and the temperature of testing, these barrier values keeps on changing. So considering the actual application area, the country where it's going to be used, we have to ensure that we put our test temperatures and RH, which is applicable for that particular application. Okay, migration and leaching. There are different standards for, it's a very, very important thing for food and pharma. There are many international standards. In this slide, I have just mentioned about the Indian standards. So there is something called, this is normally called migration. Now, there is something called a global migration. There are some standard stimulants. These stimulants are used, and then we test by weighment actually how much of this material has come from the packaging material to the stimulants. You can see there are ethanol, acetic acid, vegetable oil, and then this will sort of represent the global general application where we will be able to assess how much material is getting migrated from the packaging material. Now there is something called a specific migration also, where when we are packing a specific product or my product has a specific type of material, like some other oil or some other acid, or it can be anything. So we will do a specific migration on that using that as stimulant, and there are restriction values declared in the standards, so it has to comply to that. Along with that, there are many standards. I just want to mention you that many standards who have declared materials which are not supposed to be used in packaging materials in any form and in any layers for specific applications. These are called exclusion list. Now we have to, when I'm choosing or using a raw material for making a packaging material, we have to ensure that. Absorption and scalping, as I explained, that it's basically absorption of the material or something from the product to the packaging material. What we do is that we keep the material packed in a little accelerated condition, that is a little higher temperature, and then we keep on testing this material to normally a HPLC to see how much of that identified component is getting absorbed into the packaging material. What we do is that if the absorption is high, then we change the contact material with a different material, whether the absorption goes down. Then the compatibility study, it's been the materials are kept packed in the design packaging material inside ovens with a controlled temperature and moisture. Depending on the type of ovens available, you can have the entire oven with a particular RH, or you can control them with salt solution, as you can see in the photographs here. In India, we normally use 38 degrees centigrade, which and 50 to 55% for moist products and 90% RH for dry products. And it normally gives a 3x life cycle. Like if I test it for 1 year and it performs the test, then I'll be able to say that the shelf life will be safe for 3 years. Testing at design level. Next is communication, printing, shape. Now, a good looking product. You need to test the gloss, how glittery it is, transparency, clarity, opacity, optical density. These are the technical terms that is used to to declare how transparent a material is, which will be very important in a particular case. Haze is how not transparent it is, how matty it looks. I mean, there are products which looks, I mean, the packages which looks much better when you use something which has a little haze, which is not really transparent. Examples are silk packages of Mondelez or Cadbury's. There are many others. Scuff resistance is that if you print something onto the surface, I mean, in a packaging material, printing can be done on a transparent material and put the print inside. I mean, so that the top surface doesn't have any print, but if the materials are opaque, then you have to print onto the surface so that customers can see it. Now, on transportation or usage, there may be a rubbing coming onto the surface of this print. We need to test how resistant it is against normal rubbing. This is called scuff resistance. Stiffness, a stiffer material good, or a stiffer material can even puncture to its sister packages. So we need to control the stiffnesses very well. A very stiff, flat product looks very elegant and fine, but it costs also. So we need to test the stiffness of this material for it intended use. Then light fastness. Now, what is the light fastness is that we all know that colors fade out in exposure to light. I mean, I'm not getting into whether it's infrared or ultraviolet, A, B, C, D. Sorry, there is no D, A, B, or C, or in the visual spectra. But it's the fact that light, the colors fade out. So what we do is that, depending on the type of area where these packages will be used, we know the spectra. I mean, how much UV, how much visual radiations are there normally. So we try to create the same kind of radiations in the colors and see how much it is fading out. So what is a gloss? Gloss is a ratio of specular reflection. So light coming in, going out, this is a high gloss material, this is a little less gloss, this is a very low gloss material. And the gloss is normally tested at 20, 60 and 85 degrees. There are standards where they are testing at 45 degrees also. Why they are tested in a three different, why they are declared in three different angles is that if you see this is a semi-gloss area. The same product, when you test at different angles, you will get these curves. So at a low gloss area, you need to declare the value at 85 degrees so you can see variations from here to here. But if you use 60 degrees or 20 degrees, the variations are hardly anything. I mean, less than, in case of 20 degrees, less than even 1, and in case of 60 degrees, it's less than 10. But whereas in 85 degrees, you get a variation from say 5 to almost 60. So you get a good gradation to understand it. So the values of gloss are always accompanied by the testing angle, 85 degrees, 60 degrees or 20 degrees. So the very high gloss materials are normally declared in 20 degrees. Standard material, the first test one should do is at 60 degrees. So that was gloss. Then haze. Haze is what, how much material it is diffusing out, a transparent film. So please read this. I mean, this is not always, I mean, people who are absolutely new, first time listening to these parameters, you may find it little difficult to absorb. I mean, this is what happened to me. But this is like, if you try to pass a light through a particular transparent film, some of it will get, distributed in different angles. It scatters out. I shouldn't say it's only a refraction, but it's scattered out, depending on many things, flow patterns, particles present inside. So, if the scattering beyond 2.5 degree is a haze. What is the clarity? Clarity is a highly transparent material. The amount of light that can passes within a 0.1 degree deviation. The high clarity material you see that if you send a straight beam of light, almost everything will cross this material. So that's clarity. And opacity is that per se, even whether it is diffuse, not diffuse, gone into some other angle, scattered, amount of total light energy passing through a material is called an opacity. These indicators help a designer to choose a particular material, whether end customer is looking for a matte finish or a glittery glossy finish. He wants a fantastic transparency so that the end user can see the product, or you want a little haze in the transparent material. So it's visible, but there is a mist. So these are the optical properties. The scuff resistance, as I told you, where what we do is that we put a particular weight. It has been agreed between supplier and producer, and then we rub. We rub multiple number of times onto the surface with this using this kind of a machine, and the number of rubs it can withstand before the print goes off is declared. This on experience, we decide this depends on how the end product is going to be used. Okay. Then stiffness. The product is bent basically. It's kept it's been held in a particular jaw, and then a force is given to bend it, and that force is calculated. So higher that force required to bend it, higher the stiffness of the material is normally declared in gram force or gram centimeter, a bending moment required for that particular, in a particular gap, a particular setting of mounting this material. Light fastness, I explained to you. The accelerated exposure to control standard light simulators. We know, like there are standards Arizona, I don't remember all of them, but over the world and different places, you know the radiation that is available. So you continuously give that radiation and try to see how the color is, or the ink, or the pigment is spreading out. There is a standard called LA and B standard defined by CIE. The variation is this LA and B is indicator of how the color has changed. I don't know whether you know what is that LAB, but just if you don't know, just remember that this is a measure, like we measure length in centimeters and millimeters, weight by grams. These are the measure of measuring colors. There are three axes to it. One is L, which is the strength of the color. L is towards one tone. I don't want to use this terminology. It's called chroma and one. A for one tone and B for another tone, which are in particular direction. So with LAB, this can be variation in this parameters. This can be checked. There is something called a blue tool standard. Also, it's been used for a long time. There are certain standard blue wools produced of a particular using a particular set of pigments and all. So you keep this aside and see where it goes down. So that is standardized. That going down, different blues are scaled from 0 to 8. So you can declare the light fastness of this material. Now, convenience. So you have covered strength, you have covered the look, the printability, print carrying capacity, fade out. Now the convenience. So what is tear strength? I have already discussed that you want to open a shampoo wrap and you start fighting to tear it open. So it's important to check the tear strength. Some applications, if the stiffnesses are very low, you just cannot handle it. Like you have a pouch. The pouch is so soft, doesn't have any stiffness, you'll find it extremely difficult to pour things from there. Seal strength. You may have an application where you want to peel it open. Like I like this design of Kinder jar. As I was mentioning that when you are separating the two halves of the egg to get two containers in your hand, this thing, the seal strength between these two containers, two parts of the egg, should be such that it first opens out. The film that are used to close each of these containers, those lids, has to have a little higher seal strength with the container so that they doesn't go off when you are trying to separate. So seal strength is important. Slip resistance, COF outside, as I mentioned, that when we are stacking back in a warehouse, the slip should be such that it doesn't fall off. Or, of course, it doesn't give a very high resistance so that the workmen who are stacking them find it very difficult to put it in a proper place. So COF is important. Okay, then we go to convertibility. What is the convertibility? Now, we have designed, tested a packaging material properly for all those primary needs. Now we have to make a container out of that. How we make a container? Simplest is that we have to join, if we have to fold it and join and close, so you can create a container. The most common way of doing it in the industry is by heat and pressure. Because that is the fastest, most assured way of sealing, which is mostly being used. So there are certain factors which you need to test to ensure that my product design is perfect after it is a laminate. What is that? Siliciation temperature. At what temperature the sealing happens? If the end user doesn't know, he may seal it at a high or a lower temperature and there may be failures. And if the product is very sensitive to heat also, we need to give some sealant which seals at a lower temperature. Of course, it will go in a higher cost, but that's possible. That is seal initiation temperature. I will explain you how we declare that. Then there is something called a hot tap. Now, when I'm sealing, normally in our packing lines, we immediately pour material in that. There are packing lines which runs at a very high speed, 100 packs per minute, 200 packs per minute, 350 packs per minute, like different applications. A tea bag can be packed at a speed of 250 to 350 packs per minute, but a soap wrapper can go up to 500, 550 cakes per minute. A candy can go up to 700, 1500 packs per minute. Now, when we are heat sealing them, it's obvious that when the products are already inside, the seals are still hot. So the tackiness, when the material is still hot, when it cools down, when it's cooled down, becomes totally solid, it will give some kind of a strength. But when it's still hot, it's tacky. So depending on the application, we have to ensure that this tackiness is good enough so that there is no failure in the packages. So that's called hot tack. Then there is COF, coefficient of friction. I have mentioned it about the outside surface for stacking. For inner surface and outside surface also is important, because when I'm packing a product at a very high speed, it's probably had to pass through different rollers and slide through different passage areas. So if the slips are too high or too low, there may be failure, there may be blockages or slipping happening. Flex resistance. What is the flex resistance? In its application, a particular pack may undergo a lot of abuses, flexing, crumpling. Now, it may create pinholes in the pack depending on the material that we used, or the various properties that we have discussed, that OTR and MVTR, this resistance can get impaired. So we do a control flexing of the material and check it before flexing and after flexing so that my performance is assured. Then VOC retention. What is that? In the process of printing, in the process of laminating, that is taking two substrates together, we use solvents also. So the volatile organic content retained in the packaging material is important for safety reasons. So we have to test that. We do all these things through instruments against standards so that performance are guaranteed for the design. So what is the SIT seal initiation temperature? You plot temperature and seal strength and keep on testing. So there are different values that is considered as an SIT, and this has been decided by the user and the producer. You can say when 0.5 Newton value of the seal comes in, you can say that, okay, my seal is initiated. Somebody else can say that, oh, that's 50 grams, it's too low. Let's consider 5 Newton or 500 grams is my seal initiation temperature. I mean, that is a safe way to work it. Some cases is 50% of the seal strength. What is the seal strength? Is that if you see the graph after a particular temperature, it flattens out. You cannot go beyond that. So half of that is my seal initiation temperature. This is basically, to ensure that if you keep the temperature between this SIT and the final seal strength value or the plateau value, your seal is good enough for its application. So you need to know this graph. Then comes this hot tack. This hot tack graph shows tackiness of different cylinder materials. You see that if we increase the temperature, the tack goes down. So in a packing line, if by chance there are leakers happening because the product is being inserted when the pack is still hot, and the operator tends to increase the temperature of the sealant to ensure that it seals properly, actually he is killing the package. The hot tacks go down. So you need to clearly know what is the highest tackiness zone. Use that as your sealing temperature. There are instruments, and this is normally declared the tackiness of the seal strength after 500 milliseconds of sealing it. So a seal is created, and then you separate it after half a second or 500 milliseconds and check what is the tackiness. So that's a standard value. As I was repeatedly mentioning that we test this against standards, so everybody in the world understands what I'm talking about, and we can ensure the performance of the designed package. Gelbo flexing, I mentioned you that we need to flex material. Now, how is going to be actually flexed in the application? We really don't know. So what we do is that there is this instrument. This instrument is as per ASTM, American Standard of Testing, and when it runs, it keeps on flexing, and the two jaws goes close by and it rotates also. So each cycle has a particular movement and degree of rotation. So we keep on giving different cycles and test it. 5 cycles, there are American Standard also available. So we can give 20 cycles, 50 cycles, 1000 cycles, or even 5 cycles depending on the assessed application abuses of this packaging material. And as I said that we test before flexing and after flexing. VOC retention we normally do with a GC. I think you all know this, and we take samples. Every production lot will go through this testing, and we see that what are the levels of ethanol, and all the targeted. We know that what all materials can be there, and there are restrictions declared by the international standards and the national standards. I have mentioned one gross value of 20 milligram per square meter. So we mentioned that, and depending on the applications, it even goes down. Like these days, most of the applications for food packaging, toluene is a no-no thing, which is otherwise a very popular and being used type of solvent for making packaging material. Okay, so that was design part. assurance part. We test, we design, we test, we retest and ensure that I am assuring these properties in my packaging material, whether it is print, whether it is strength, whether it is barrier, whether it is leeching, whether it is scalping, everything. Now, once that has been done, then when the materials are produced, we do some incoming test. Like before using, we basically check the substance weight, how many inflexible packaging is GSM, grams per square meter, what is its weight per square meter of material, what are the dimensions, as I said, the length, width, thickness of the material, bond strength, because that may be a variation point. Print quality, which is obvious, we must ensure that that's also a variation point, how the print compared to an agreed standard, and if there is only odor coming in, we ensure it through a GC test. End user can use a GC test, or there are other simpler tests to ensure that the odor is controlled. When the odor, a minute odor, is very, very important for this application. Then in process, we do a leak test, a drop test, and a visual inspection of the material. Leak test is basically, though we have assured the seal strength, seal initiation temperature, hot tax, everything, but still this is the variation point because it will actually depend on the pressure provided by the sealant jaw and its temperature. So it's important to check leak. It's normally done through a vacuum test. And then a drop test. There are standard tests of dropping a material from a particular agreed height at a number of times and to different phases and see that it doesn't fail. The toughness of the material has to be good enough so it doesn't fail if it is important. Then visual. Generally there should not be any problem in the whole thing. Okay, so that was what all we test for assuring that my product will conform to the indented need of this application. Now, still, unfortunately, there are problems that is happening in the life cycle of packaging materials. So we use specialized material to find out what has gone wrong. Very commonly used are DSCs for checking the thermal properties of material. I'll just discuss what we actually, how we actually use. Infrared spectrometers, normally Fourier transformed IR spectrometers and IR microscope is used for this application. Then we can have all these tests of tensile, bond strength, seal strength, puncture, everything we can test. And then very specific applications we need to use an HPLC, NMR, and atomic absorption. I don't know whether they are still used these days. But high-end IR spectrometers, your X-rays, scattering, and these kind of high-end instruments are used, but not very regularly. Very, very specific need for in application of packaging material. So how we do it? What we do it in DSC is that we take the thermal properties, heat absorption, and peaks. Then we can check if there is something wrong has happened to the sealant or the plastic material or the polymer that we have used, designed, indented to use or designed to use in this material, whether there is any variation. And if there are multiple materials, I've just shown one plot, there may be multiple peaks. And if you know this material, you know the properties of this material from the peak temperature and the heat absorption, the joules per gram or something, we can make an assessment at what percentage these materials are present, and we can compare whether it is conforming to the way we designed it or not. Similarly, IR spectrometer is also used along with the DSC, so that we get a plot absorption, IR absorption plot, and we know why the absorption happens. The packaging material manufacturers have a good library of such plots of commonly used materials in the industry, and we compare and we want to see if there is any deviation in a variation. And sometimes if there are unknown peaks coming in, then we break our head to find out what are the functional grooves present, why it has come. These are mostly used for testing unknown material, testing material which is not performed, to make sure that these chances of occurring non-conformance doesn't happen in future. Okay, that's all I had to say. And though we started late, I think I've managed it. I've gone a little fast. Anybody have any questions, please speak out. Yeah, I'm just repeating that I'm through whatever I had to say and explain. If I have gone a little fast, I'm sorry, but I mean, if you have any queries, any clarification required, any of you, please speak out. Okay. In that condition, in that case, can I consider this to be over? Mr. Rao, if you are there, please confirm.